Hi everyone, this is MathsForUni. Today we'll be looking at question 7 from lecture 9 of our Udemy course. If you enjoy this content, then please consider liking and subscribing, as well as checking out our full Udemy course. The link is in the description. The question says, for the matrix A, which is 1, 2, minus 1, 0, 3, 4, minus 5, 2, 1, show that a cubed is equal to 5a squared plus 6a minus 60i. And the question also has a hint, which is there's a fast way and a slow way. So first, the slow way is to compute a squared and a cubed and verify that both the left hand and the right hand side of this result agree with each other. I would suggest that you actually try this method as a verification of the alternative method that we'll consider instead, which is using the Cayley-Hamilton Theorem. We begin by finding the characteristic equation of the matrix A. We do this by solving for the eigenvalues which come from the equation determinant of A minus lambda I is equal to 0. The matrix A minus lambda I looks like, based on the matrix A, 1 minus lambda, 2 minus 1, 0, 3 minus lambda, 4, minus 5, 2, and 1 minus lambda, i.e. a minus lambda goes on all of the diagonal elements from this minus lambda I here. If we then take the determinant of this matrix, then we will get determinant of A minus lambda I is equal to the factor 1 minus lambda times by the determinant of 3 minus lambda, 4, 2, 1 minus lambda, and then we have a minus 2, and then we have a 0, 4, minus 5, 1 minus lambda, and then finally we have a minus 1 with 0, 3 minus lambda, minus 5, 2. If you're not sure how to expand the determinant of a 3x3 matrix in this way, then check out our video in the course on taking determinants of 3x3 matrices. Next, we continue by finding the determinant of the 2x2 matrices here, here, and here. This gives us 1 minus lambda, and then we'll use a square bracket, and we'll have 3 minus lambda, 1 minus lambda, and a minus 8. Then a minus 2 with, again, square brackets. And we have this 0 here is going to result in nothing for this term, but we'll get a plus 20 from this term here. Then we have the minus 1, and a similar thing happens for this here. And so we are left with, let's have a look, 5 times 3 minus lambda. Next, we can expand out this square bracket here because there are more than one term in that square bracket. And so we get 1 minus lambda all squared from the extra 1 minus lambda in here with a 3 minus lambda and then a minus 8 1 minus lambda. Let's also expand out these things here, and so we have a minus 40. Let's make that look more like a lambda, and we have a minus 5 times 3 minus lambda. To apply the Cayley-Hamilton Theorem, we will want to expand this out in full and obtain a cubic equation in lambda. Since det of A minus lambda I is equal to 0, which is the characteristic equation, we set this equal to 0. Again, That's just from using this equation that we're seeking to solve here. We've calculated this and got to the point of this, and then we set it equal to 0. But next we're going to expand. If we do this first by expanding out as much as we can in one go, let's expand this. And so we have 1 minus 2 lambda plus lambda squared. We'll keep the 3 minus lambda for a moment, but we'll expand that after. Let's continue to expand as we go. Minus 8 plus 8 lambda, minus 40, minus 15 plus 5 lambda. Again, this is equal to 0. So let's put a right arrow there for this to be an equation. Next, we expand out these brackets here, and so we will have 3 minus lambda minus 6 lambda plus 2 lambda squared plus 3 lambda squared minus that lambda cubed. And then we have, let's collect these things kind of all together. In doing so, we will get a plus 13 lambda from the 5 lambda and the 8 lambda, and then we'll have a minus 63 from all of our constant terms here. Again, this is still equal to 0. If finally we collect all of these terms together, we will get minus lambda cubed plus 5 lambda squared plus 6 lambda minus 60 is equal to 0. The Cayley-Hamilton Theorem says that a matrix satisfies its own characteristic equation. So we can replace the lambdas in this equation with the matrix A. This will give us minus a cubed plus 5a squared plus 6a minus 60i is equal to 0. The constant term here picks up an I for the identity matrix to ensure that this is a matrix equation. Finally, we rearrange to put the a cubed onto the other side. We have a cubed is equal to 5a squared plus 6a minus 60i. So indeed, we have shown what we wanted to show up here. Now, this method may or may not be faster for this particular matrix, but as the size of the matrix increases, this method should win over direct calculation of the powers of A. In this example, all we need to have found was a squared and a cubed, but for a matrix of, say, size 100 by 100, you'd have to calculate all of the powers of A, most likely, between A and A to the power of 100. And so this method should win. If you've enjoyed this content, then please consider liking and subscribing, as well as checking out our full Udemy course. The link is in the description. Thanks for watching, and goodbye for now.